Hi guys, sorry for the delay. My mum's been over and doing some renovating, which means I haven't had much time to myself. Still, I have a much better flat now than when she arrived, so I'm not complaining. Might even be worth showing my face once I get the proper setup. And speaking of setup, like my new logo, I have fellow seeker Walter Pedro, aka Google, to thank for it. Please let both of us know if you like it. And on with the countdown. Juno Jupiter? It's almost an insult to call Jupiter a planet. It's essentially a miniature solar system, a magnetically active monster lording over a retinue of geologically active worlds, one of which may be home to life. Jupiter comprises 60% of the mass orbiting the Sun, and other than Saturn, which is itself a downsized solar system only on a smaller scale, the rest of the planetary material, including us, might as well not exist. Until very recently, it wasn't even clear if Jupiter was a planet at all. Well, not to me, which is why I was looking forward to the Juno mission. Now mostly famous for providing the astounding and unexpected images of Jupiter's Van Goghian polar regions, Juno's primary mission was to employ a polar orbit to study Jupiter's interior, and finally determine if it had a core, like a planet, or was simply a drop of hydrogen in space, like an unambitious star. Not that this possibility was considered likely. A Juno mission member I bumped into whilst volunteering at the Greenwich Observatory earnestly informed me that if Jupiter was not a planet, then everything we thought we knew about the solar system was wrong. So, is it? Well, after 3 years of probing, Juno eventually concluded that Jupiter indeed possesses a core. But it is, in the words of NASA, fuzzy, extending outward to nearly half Jupiter's diameter. It's as if Jupiter knows it's a planet, but doesn't want to admit it. With its primary mission seemingly over, Juno began 2021 by catching what is becoming an increasingly frequently observed phenomenon: a meteoroid impacting Jupiter. Juno did not literally see it. It would have been a pretty staggering coincidence if it did. Instead, the meteoroid showed up as a massive spike in brightness outside Jupiter's auroral zone. At first, the team assumed it had to be lightning, but lightning has a different spectral profile and is nowhere near as powerful. The impactor was believed to weigh about a metric ton. Because Juno is so close, it can see impacts far smaller than those observed previously on Jupiter. The team estimates that such small impacts strike Jupiter about 24,000 times a year. But this was the first that Juno had observed, because it only spends a tiny fraction of its time actually facing Jupiter. With its main job completed, Juno's primary focus now is Jupiter's aurorae, which, unlike those on Earth, are permanent features of its atmosphere. Earth's aurorae are primarily caused by the solar wind, but Jupiter forges its own, thanks to a magnetosphere 20,000 times stronger than Earth's, though precisely how is still not certain. It is known that the solar wind still affects Jupiter's aurorae in numerous ways. In March, Juno identified a weak expanding wave in Jupiter's aurora that appears to originate at the point 5 million kilometers from Jupiter, at which its magnetosphere touches the solar wind. In April, a team at the University of Alaska announced that they had discovered the reason for Jupiter's unique auroral structure. On Earth, the aurora forms a circle around the pole, like a crown. But on Jupiter, the aurora covers the entire pole, like a hat. The team ran a simulation that showed that, thanks to its powerful magnetosphere, Jupiter's aurora is less likely to be disrupted by the solar wind, and so persists where others do not. This persistent aurora has been suggested as the reason Jupiter's equator is far hotter than predicted. In 2021, a team modeled the heat transfer from the aurora and found that it was great enough to heat Jupiter's entire upper atmosphere. In May, Juno turned her attention to Clyde's spot, a white oval in Jupiter's atmosphere discovered by amateur astronomer Clyde Foster in 2020. Clyde spot is believed to be a smaller scale version of Jupiter's Great Red Spot, an eruptive spew of material from Jupiter's depths. These storms are usually temporary, but by 2021, Juno showed that Clyde spot had grown to twice its original size and had developed a complex internal structure. Whether it will follow the course of previous white ovals and become a new red spot remains to be seen. As well as determining the nature of Jupiter's core, Juno's other prime mission was to map its cloud tops in 3 dimensions. And this year, teams released the accumulated results of 5 years of observation. Jupiter's clouds are divided into 2 easily discernible forms: white zones and dark belts. When imaged in microwave light, the colors switched, with the zones appearing dark and the belts light. This indicated the presence or absence of ammonia, which absorbs microwave light. But when Juno peered 65 kilometers down, it got a surprise. The belts and zones were inverted again, the zones light, the belts dark. This suggested that 65-kilometer tall atmospheric cells, similar to the Hadley or Ferrel cells on Earth, were carrying ammonia from the depths to the, for lack of a better word, surface. The teams also revealed that the Great Red Spot is far thicker than originally thought, descending to 500 kilometers depth, though its vast area means that, relatively speaking, it is still barely as thick as a pancake. Black holes are awesome. Sorry, couldn't come up with a better title. Not that anyone watching this video would likely disagree. Black holes are awesome. They're awesome in their scale, both minute and gigantic. They're awesome in their power, which can be seen across the universe. And they are awesome in their mystery, the closest to the truly sublime that exists in our current conception of the universe. For it is here, within black holes, that the hard, relentless mathematical certainty of the modern world literally implodes. Not even Einstein could answer the infinities at the heart of black holes, and their very existence hints at possibilities and new levels of reality, a fact I will return to later. 2021 saw many discoveries that, if anything, doubled down on their infuriating mystery. By knowing more, it sometimes seems as if we know less. For instance, until 2021, our knowledge of black holes comprised 2 very different entities: stellar mass black holes, which form from the deaths of large stars, and supermassive black holes, which reside in the hearts of galaxies and were hundreds of thousands to billions of times the mass of our Sun. The origins of stellar mass black holes are pretty solidly attested. We may have even photographed one's formation. But the origins of supermassive black holes are frustratingly opaque. To this day, we still don't know how they form, or their relationships with the galaxies they reside in. But given the sheer scale of the difference between stellar mass and supermassive black holes, we could at least operate on the assumption that they were fundamentally distinct entities, in both nature and formation. But in March, a team of astronomers in Melbourne announced the discovery of a black hole of only 55,000 solar masses, barely a quarter the mass of the smallest known supermassive black hole. Unfortunately, this so-called intermediate mass black hole was snapped via a gravitational lensing event, and so is unlikely ever to be observed again. But nonetheless raises the question, what the living heck is it? The team suggested it may be the building block of a future supermassive black hole, which is all well and good but doesn't really answer the question. But that same month, Keijun Chen, a research fellow at AISA, Taiwan, thought he may have the answer. Population 3 stars. Our Sun is a population 1 star, which means it is very high in what astronomers call metals, i.e., anything heavier than hydrogen or helium. At just 5 billion years old, the Sun formed as part of the 3rd generation of stars to be born in our still relatively young universe. The previous generation, called Population 2, are far poorer in metals, as their comrades had to die to enrich the universe with their metallic dust. Population 2 stars, which can be up to 12 billion years old, are the oldest stars ever observed. But a third, primordial population is thought to have existed at the universe's birth. These stars, if we ever develop telescopes powerful enough to detect them, will have, or had, no metals at all. They will also be gigantic. Their lack of metals would have meant that they would fragment from nebulae at much larger sizes, tens or hundreds of thousands of times the mass of the Sun. These stars would barely have lived at all before dying and then transforming into gigantic black holes, much like the one observed by the Australian team. On the opposite end of the size spectrum, in April, a team at the University of Ohio identified one of the smallest black holes ever discovered, located in the constellation Monoceros, and appropriately nicknamed the Unicorn. At just 500 parsecs away, that's 1,500 light-years, it is the closest black hole to Earth ever found. And at just 3 times the mass of the Sun, it is titchy. Obviously invisible to optical telescopes, it was detected thanks to the red giant it currently orbits, at one time formed a binary star system with. If it is indeed a mere 3 solar masses, that would make it the smallest black hole ever found. The next largest is just 3.8 solar masses, while the lower limit for a star to become a black hole is believed to be about 2.9 solar masses. There is some speculation that stars cannot form black holes at such small masses, and that they must form from colliding neutron stars. In February, a team employing the Galactic and Extragalactic All-Sky ALMA MWA survey, or GLEAM, which we will see again later in this video, studied the emissions from young versus old galaxies to see if they could map their evolution over time. What they found flabbergasted them. Of the 554 baby galaxies surveyed, 123 appeared to wildly fluctuate in their brightness over the course of years. This was insane. Galaxies are gigantic objects. By their standards, our own is not particularly big, but it still takes light, the fastest thing in the universe, 300,000 years to cross it. You would expect any event affecting an entire galaxy to take place on comparable or even longer timescales. Galaxies do not twinkle. Except, perhaps they do? Twinkling is distortion by Earth's boiling, roiling atmosphere, but modern telescopes are calibrated to account for that. However, the Milky Way itself has its own atmosphere, and the light from these distant galaxies has to travel through it to reach our eyes. Perhaps these distant galaxies were behind some obscuring cloud of gas. Another possibility is, of course, black holes. Perhaps the supermassive black holes at the centers of these galaxies may be what are called blazars, producing active jets viewed top-down from Earth, like the barrel of a gun. Because all we see is the tip of a relatively small jet, changes can take place over relatively small timescales. Or perhaps they could be burps, sudden eruptions of material within black hole jets. We still don't know. The measure of a comet. Of all astronomical phenomena, none have longer and more thoroughly ignited the human mind, for better or worse, than comets. For thousands of years, comets, or bearded stars, were seen as interlopers, omens, portents, and disasters. The word disaster, in fact, means evil star. Even today, they can still trigger paranoia, madness, and death. For scientists, however, they fire imagination for completely different reasons. Comets represent a largely unspoiled sample of the solar system's construction material, a project that, as the numerous comets that have struck Jupiter attest, is still ongoing. This year saw many developments in our discoveries and understanding of these curious little ice balls. One of the most peculiar things about comets is that, much like planets, we don't have a meaningful definition for them. According to current definitions, a comet is a comet if it forms a comet's tail. This makes a certain amount of sense. After all, it's usually impossible to tell just from looking what an object is made of. Even spectroscopes can only scan the surface and say nothing of the overall composition. So the only way you can tell if an object is a comet or an asteroid is if it acts like a comet. But such a conception leads to absurdity. Take the objects known as centaurs, which most astronomers agree are just comets that don't come close enough to the sun to form tails. Except when they do, and that means, given their long orbital periods, they are frequently discovered years or even decades before such formations occur. It can lead to centaurs, such as the most famous one, Chiron, being declared both asteroids and comets. In June, the gigantic long-period object 2014 UN-271, nearly 10 times the size of Halley's Comet, erupted into a comet, which allowed it to be granted the cometary name of Bernardinelli-Bernstein, and made it the second largest comet ever discovered after Chiron. It should be said that Chiron, whilst being the very largest comet, is not the largest centaur, merely the largest to show cometary activity. Don't worry, BB, as the comet is nicknamed, is not coming near Earth. It is expected to swing around the orbit of Saturn sometime in 2031. Its orbit is identical to those of many long-period comets, with the farthest distance from the Sun of over 50,000 AU, square within the Oort cloud. But if we hadn't seen that momentary cometary burst, it would never have been called a comet. To muddy the waters even further, it turns out centaurs can form tails before they come anywhere near the Sun. Models run by Eva Lilly et al. In September suggest that some centaurs contain amorphous ice that coalesces at temperatures below 150 kelvins. This form of ice traps gas, which, should the centaur be tugged by a giant planet, it releases as the jostle converts the amorphous ice to normal crystalline ice. I've mentioned these kinds of explosive cometary events before, particularly with Schwarzmann-Wachmann, whose explosive outbursts continued into this year, though it seems they are far more common than we might assume. On top of that, in May, a team at the European Southern Observatory's Very Large Telescope in Chile announced that heavy metals like iron and nickel have been detected in the atmospheres of comets. No one is entirely sure how iron and nickel can sublimate so far from the Sun, but it appears to be a universal trait. A separate study detected iron and nickel in the interstellar comet Borisov, and this year, a study of meteoritic dust and Antarctic asteroids using laser spectroscopy found that it contained large amounts of supposedly cometary material, while another study found that asteroids themselves can have active surfaces, indicating that the difference between asteroids and comets may not be all that clear after all. But when it comes to comet versus asteroid, the one question everyone wants answered is, which one killed the dinosaurs? Well, I'm happy to say that Avi Loeb, the Fred Hoyle of our generation, believes he has an answer. In February, he and Amir Siraj of Harvard published a paper in Nature arguing that sun grazers, comets known to come close to the Sun in their orbits, could break into swarms which could increase the chances of an impact by a factor of 10. Comets are traditionally considered bad candidates for terrestrial impacts, simply because they come from much farther away and thus have a much wider range of orbits, a fact Loeb himself agrees with, pointing out that statistically, an asteroid is more than 10 times more likely to strike the Earth than a comet. However, once you factor in the unusual carbonaceous chondritic composition of the Chicxulub impactor, the likelihood of a strike falls to the cometary probability of about once in 3.5 billion years. In other words, not likely to happen in the age of the solar system. Given that the only comet sample returned to date, stardust, revealed a carbonaceous chondritic composition, comets appear far more likely to be so formed than asteroids. The most surprising element of the article, at least to me, was the computer model, in which Jupiter, long seen as the solar system's benign comet slayer, in fact throws comets inward toward the Sun, increasing the likelihood of a collision. Believe me, I was as surprised as you to learn that the whole good Jupiter idea was a load of hooey. But it is backed up by previous models. All the more reason we should be studying comets. A flash in the dark. My idol, Isaac Asimov, reportedly once declared that, quote, The most exciting phrase to hear in science, the one that heralds new discoveries, is not Eureka, but that's funny. And in November, a group of radio astronomers in Australia had a very funny thing happen. In a study of 24 hours of archival low-frequency radio data from the Murchison Wide Field Array, which I still can't believe is a functioning telescope, the team identified a repeating radio emission across a broad frequency that lasted between 30 and 60 seconds at a time. The signal, called Gleam X J16275.5/3523504.3, was only 4,000 light-years away, our backyard in galactic terms. What distinguished Gleam X was its interval, a full 18.18 minutes, an interval for a repeating radio emission that had never been seen before. Also, the low-frequency radio wavelength is a region of the electromagnetic spectrum traditionally considered quiet. Gleam X was moderately bright, about half the maximum expected for interstellar radio sources, and far brighter than any known source at that frequency, such as flare stars, magnetic exoplanets, or white and red dwarf binaries. In addition, these signals would be circular in form, while Gleam X was linear, or flat, suggesting its originating magnetic field was intensely strong. Gleam X is also intensely regular, to an error of 1 in 2 million, and so is likely from a rotating or orbiting source. Since the object is believed to be no more than 0.5 light seconds across, or about the diameter of Jupiter, rotation seems more likely. By now, you're probably all crying, "Pulsar!" And normally I'd be right there with you. Except no pulsar rotates even remotely that slowly. The slowest known pulsar, identified in 2018, rotates once every 5 seconds. Of all identified interstellar radio sources, the one that most closely resembles this signal's waveform is GCRT 1745, a radio source near the galactic center with a 77-minute periodicity that is believed to be a long-period magnetar, a recently deceased pulsar still spattered with its original stellar matter, whose infall causes its rotation to slow over time, and also supercharges its magnetic field until it is powerful enough to magnetize every atom in your body. If Gleam X is a magnetar, however, it would be one of the dimmest on record, and also by far the closest ever found, less than half the distance of the current closest. And finally, magnetars emit X-rays, but Gleam X does not. Unfortunately, Gleam X has not been redetected to date, but the team are on the lookout for it. When the incomparable Jocelyn Bell discovered the first pulsar in 1967, she nicknamed it LGM-1 for Little Green Men, because its periodicity seemed artificial. Astronomers are more cynical these days, but it's still nice to get a shiver of the old magic. Unlike previous years, I couldn't come up with a list of my own, so asked around for others' opinions. I got way more than 10 responses, but felt they all deserved to be heard, alongside some follow-ups from previous lists. So, in no particular order, in July we saw the detection of a moon by an amateur astronomer. It wasn't a discovery. The 3-kilometer-wide moon of Jupiter had already been found in 2003, but the fact that amateurs are moving into realms formerly occupied by professionals is a good sign that an explosion of moon discoveries is due. In August, it was revealed that yes, the dimming Betelgeuse experienced last year was likely due to a giant star spot. Or a dust cloud, if you believe another team. Really, the answer is we still don't know. More importantly, the second team also found that Betelgeuse was still in its helium-burning phase, and so unlikely to explode for about 100,000 years. Relieved? Or disappointed? In October, Breakthrough Listen had to announce that the detection of the signal supposedly from Proxima Centauri was, in fact, most likely Earthbound. Similar signals were detected in the data archives that appeared even when the telescope was turned away from its target. Not a surprise, perhaps, but sad. Also in October, Lillian Burkhardt, a doctoral candidate and graduate student researcher at the University of Hawaii, found evidence in Cassini images of strike slip faulting, similar to the San Andreas fault, on Titan. So, as if it needed to be any more Earth-like, Alongside rainbows, lakes, and volcanoes, Titan also has earthquakes. Another brick in the road. The last 200 years have seen the greatest increase in human wealth and prosperity since we came down from the trees. This wealth has largely been the reward of technological innovation, which was in turn the fruit of scientific investigation. It was as if, when Galileo turned his telescope to the sky in 1610, a blindfold fell from human eyes. Barrier after barrier fell, as once esoteric ponderings gave way to systematic predictive disciplines. Astronomy in the 1600s, chemistry in the 1700s, biology in the 1800s, geology in the 1900s, psychology in, well, anyway, the point is that the godlike level of luxury now enjoyed by the common man lucky enough to live above the 30th parallel is largely due to the unheralded efforts of hundreds, thousands, and now millions of scientists. For the last 400 years, science has effectively offered a trade, a higher standard of living in exchange for your moral and existential security. You may have noticed, though, that our standard of living has been stagnating recently. There are many reasons for this, but one of them is that science is in something of a rut. I don't want to accuse science of not trying. Billions of dollars and man-hours have been spent in the pursuit of new scientific breakthroughs, many of which have made their way into our lives. But if you look at the 50 years between 1922 and 1972, and compare them with the 50 years since then, it's clear something is missing. The bedrock of science is physics. All other sciences flow from it, as it concerns itself with the ultimate building blocks of the universe. Glibly described as the study of energy, it is better described as the study of nature itself. Nature in its original sense, that which physically exists. Today, physics is, as it has been for a century, divided into two irreconcilable kingdoms: general relativity, which concerns itself with the very large, and quantum mechanics, which concerns itself with the very small. Each of these theories has been tested to the limits of human effort and ability, and survived. But both, as written, cannot be true. In relativity, reality is smooth and continuous. In quantum mechanics, it is broken into finite bits or quanta. In relativity, cause and effect can be predicted. In quantum mechanics, they can only be guessed to within a certain probability. In relativity, the speed of light is an absolute limit nothing can exceed. In quantum mechanics, particles can instantly influence each other over distances however large. The last century has been one long, laborious attempt to bring these two realities into sync, and to date, it has failed. The great successes in physics in recent decades, the top quark in 1995, the Higgs boson in 2012, were simply confirmations of what we'd already suspected. On the opposite end, dark matter and dark energy continue to elude explanation. Our answer to this problem so far has been to build bigger and bigger tools. At the small end, particle accelerators, which smash bits of atoms together to produce smaller particles. At the large end, telescopes, to map the effects of gravity at the universal scale. Particle accelerators have so far shown us the mechanics of three of the four forces that we know govern the universe: electromagnetism, which holds matter together and is carried by the photon; the weak force, which governs the identity of subatomic particles and is carried by the W and Z bosons; and the strong force, which holds the atomic nucleus together and is carried by the gluon. The fourth, gravity, despite being the most familiar, is still a mystery. Does it too have a carrier, the fabled graviton? The problem is that according to Einstein, the force of gravity doesn't actually exist. It is merely the result of mass's curvature of space-time. It is possible that space-time itself is quantized, the famous quantum foam, but if so, it is on the scale of the Planck length, a distance as far from our current observational limits as you are from the edge of the visible universe. One possible solution at the large end is to look at black holes. The most obvious obstacle in unifying gravity with quantum mechanics is that gravity is an incredibly weak force. 10 to the 36, that's a trillion times weaker than the electromagnetic force. At the quantum level, it may as well not exist. But black holes are the region at which gravity is compressed to the quantum realm and becomes the equal of the quantum forces. The first person to unify the quantum realm with that of Einstein, at least in theory, was Paul Dirac, whose Dirac equation, which applied the famous E=mc² to the electron, would lead to the discovery of quarks and antimatter. One side effect of Dirac's calculations was that it necessitated the existence of so-called virtual particles. Because quantum mechanics allows for any possibility provided it is not intruded upon by the macro world, a particle may be traveling faster than light, which would mean that, and thank you to Lawrence Krauss for explaining this in a way that I have a hope of understanding, should it have any impact on the universe, one could observe the effect before one observed the cause, which in turn would mean that the particle, effectively, was traveling backwards through time. And since a negatively charged particle traveling backwards through time is functionally identical to a positively charged particle moving forwards through time, such an event effectively turns a negatively charged electron into a positively charged positron. For a brief, unmeasurable moment, an antiparticle is created out of nothing, which would then annihilate itself and its electron partner, as matter and antimatter do, before it can affect the universe. Because quantum indeterminacy means that all possible states of an atom occur at once, that would mean that virtual particles must exist everywhere. Dirac did not believe in virtual particles. He thought they were just a mathematical ghost that would be banished by later experiments. But later experiments showed them to be real, as their opposite charges reacted differently to the positively charged atomic nucleus. But, pondered a young physicist named Stephen Hawking in 1974, what would happen if one of those virtual particle creations occurred near a black hole? In that case, the antiparticle would be pulled beyond the event horizon before it and its partner could annihilate, leaving the other to fly away to infinity. Since the energy to fly away can't come from nothing, the particle steals that energy from the black hole, thus depleting its mass. This is an approximation. The actual description is way more complicated. If you want to hear it, I suggest watching this PBS Spacetime video. Hawking found that the equations describing such interactions were identical to heat radiation, and that black holes, for all intents and purposes, emit an almost imperceptible glow. A glow as homey as 2/1000th of a Kelvin. And here, finally, is where the first of our bricks is laid. In September, Professor Javier Calmet and Volkert Kuipers at the University of Sussex offered the first elaboration on Hawking's discovery. As they ran corrections to Hawking's calculations of black hole entropy, a strange number kept reappearing in their equations. This number, the team realized, was identical to a pressure exerted by the decaying black hole in line with Hawking radiation. Black holes don't just radiate. That radiation exerts pressure on its environment. Not perhaps the mightiest bound into the unknown, but a bound nonetheless. Another direction into the unknown is down, into the subatomic. And until the Large Hadron Collider was built in 2008, the best place in the world to do that was Chicago's Fermi National Accelerator Laboratory, or, affectionately, Fermilab. Despite its name, it was not founded by Enrico Fermi, who had been dead for 15 years by the time it was built. It is nonetheless a fitting name, since the complex wouldn't be there without him. Anyway, in April, a team at Fermilab announced that they had a major "that's funny" moment involving muons. If you've never heard of a muon, that's hardly surprising. Essentially electrons, but 200 times heavier, they're one of those elementary particles that, as far as we can tell, aren't made of anything else, but don't seem to do anything particularly useful. Usually only seen when pions, quark-antiquark pairs, decay, they survive for about 2 microseconds before decaying into other subatomic particles. How can an elementary particle decay? Excellent question, which I will refer to the video above by the ever-eloquent Sabine Hossenfelder. You might not agree with their arguments, but they do represent the current scientific consensus. Fermilab's Muon G2 experiment, which began in 2018, uses a 50-foot magnet, that's about 15 meters, to see what muons do when caught in a magnetic field. Muons, like electrons, react to magnets, and one way they do so is by precessing, or wobbling slightly in response to increased magnetic strength. Additionally, the pop and fizz of virtual particles makes magnetized muons bob up and down like buoys in an ocean, only at nearly the speed of light. All this can be accounted for, but it turns out that once all the known culprits are added in, appear to be bobbing a little too groovily. This replicates, to far higher precision, the results of an experiment conducted at Brookhaven Laboratory in 2001. In fact, the magnet was physically transported from Brookhaven to Fermilab in 2013. So it does not appear to be a fluke. Something in the shadows is prodding muons in ways we can't explain. While claims of a new force of nature are a bit premature, it is clear that something new is rising. Particle physics requires levels of certainty that dwarf our usual understanding. To be considered a discovery, a finding has to have an uncertainty probability of 5 sigma, which translates to 1 in 3.5 million. This finding has a value of 4.2 sigma, or about 1 in 40,000. It may take another run before we're sure, but if something is down there, it seems only a matter of time before we catch it. It is an interesting historical quirk that the advancement of science has frequently coincided with some of the darkest periods in human history. The great debates of the Athenian Agora took place as the city-state fought for its life in the Peloponnesian War. The findings of Tycho, Galileo, and Newton emerged as Europe tore itself apart in religious conflict. The formulation of quantum mechanics and relativity spanned 2 of the bloodiest wars committed by humanity. Current events suggest that history is about to rhyme again. Here's hoping the dividend is worth it.